Last time we looked at how to solve some fairly simple algebra problems, and we learned a problem-solving process to take us through that would hopefully enhance our chances for success. Today we're going to look at two other more challenging types of algebra problems. You've seen them before in probably Algebra 2 and maybe somewhere else, but these are a little bit more challenging than the ones we were looking at yesterday, but they're ones that are going to come up time and time again throughout this course. So once again, you need to be familiar with the techniques that we're using. So let me go ahead and do what I did yesterday. Let me give you some given information, some unknown information, and a starting equation. And let's say we know the following. In fact, let me make this problem more physically significant by telling you what's going on here. Let's say you were to stand on top of a 5-meter tower. Right, so you're 5 meters off the ground. And to put that in perspective, from the floor to the ceiling is roughly 3 meters, so we're maybe not quite 2 stories up in the air. And let's say you stand on top of that tower with a baseball in your hand. There's the baseball. And let's say you wind up and you throw that ball straight downward in such a way that when it leaves your hand, it's already moving with an initial velocity of 3 meters per second in a downward direction. Now that's not really that fast. That's only maybe about 7 miles per hour or so, but the point is it's leaving your hand with a speed. So in terms of given information, we know the distance the ball has to travel before it gets to the ground is 5 meters, and we know its initial speed, v sub I, is 3 meters per second. The other thing that you'll learn is while that ball is moving downward, it's under the influence of gravity. And in the absence of significant air drag, gravity always accelerates things at the same rate, which in our location is right around 9.80 meters per second squared. So that's the rate at which it's gaining speed as it moves towards the ground. What we would like to know is how much time does it take to get there? How long is it in the air? Given the fact that it has 5 meters to travel, it starts out at 3 meters per second, and it's accelerating at 9.8 meters per second squared. The starting equation that I would give you to solve this problem would look something like this. D is equal to v sub I t plus 1/2 at squared. All right, so this is not made up. This is a problem that you will be encountering again in actually just a few weeks. We need to solve it for time, and as you look at the equation, the first thing you realize is that the time t shows up 2 different places. It shows up here, and it also shows up there. So maybe the first thing you think of is possibly factoring out the time. I mean, that worked in the past when we had the unknown at 2 different places. So let's give that a try. We'd have t times the quantity vi plus 1/2 a times t to the first power. All right, well that's nice, but to solve that thing for t, if we divided both sides by everything in the parentheses, we'd have d over v sub I plus 1/2 at, but that's not really solved for t, because I still have the t over here. So I can't go plugging in the numbers and get the value for t. So that wasn't particularly useful. So we might as well get rid of that and go back to the starting point. You know, maybe we want to go back to here and try something else, or maybe we want to go back to the original equation. Somebody might say, well, what if you divided every term in the equation through by t? Let's go back to the very start. Now, what if we divided both sides of the equation, every single term, by t, which is the same as multiplying by 1 over t? Would that do it? Well, on the right-hand side, we cancel out the t with the v sub I and just get v sub I, plus we cancel out one of the t's and 1/2 at squared and just get 1/2 at. Now, that's good. Only one t over there anymore. But now on the left-hand side of the equation, we'd be left with d divided by t. That's almost worse than what we started with, because now we have the unknown in the denominator. So that would be a mess to try to go any further there. Yep, that approach isn't going to do us much better. You could sit here with this problem for several hours trying to do the types of things that we just did. To no avail. Because this is a problem that if you don't approach it from the correct technique, you're probably not going to get the correct answer. And let me mention, too, that this is something that you've seen before. This is something that you all know how to do. But maybe if we wrote it in a slightly different form, you'd have a better chance. So let's write it this way. Let's subtract d from both sides. And let's write it as 1/2 at squared plus v sub I t minus d is equal to 0. Does that help at all? Now, bear in mind that the thing we're trying to solve for is t. T shows up right here, raised to the second power. T shows up right here, raised to the first power. And then in the next term, it doesn't show up at all, because all we have is a constant. Now, where in your mathematical experience have you encountered an equation where you have the variable, and usually mathematicians use x's, not t's, because, well, I don't know why, because they like to use x's, I guess. But where have you encountered an equation where you have x to the second power, x to the first power, and a constant all in the same equation? Well, if you remember, those were called quadratics, quadratic equations. Maybe you had something like this. Maybe you had 3x squared minus 4x plus 5 is equal to 0. All of you have seen those types of equations before, and all of you have worked on those before. If you were given something like 3x squared minus 4x plus 5 equals 0, to solve for x, you'd have two choices. One of the things you might try to do is to try factoring it. And probably you spend lots of time in algebra learning how to factor equations like that. In physics, you're going to find, though, that most times equations aren't going to factor. And the reasons they're not going to factor is because most of the values that you're going to be given are going to be values that involve decimals. They're not going to be nice whole numbers like you're used to dealing with in math class. The other approach, remember, that you learned is that any time you had an equation in the form ax squared plus bx plus c equals 0. In other words, anytime you had a general quadratic like that, which is what we have, you learned out there's a formula called the quadratic equation, or the quadratic formula, which allows you to solve for x. And if you remember that formula, it said x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Right? That's the quadratic formula. That's something that all of you should know. In fact, that's something that when I was in high school, my Algebra 2 teacher tried to drill into us that much that if he saw you coming down the hall, not during class, but if he just saw you coming down the hall, you were required when you saw him to recite the quadratic formula. In fact, kids would duck into bathrooms and everywhere else to try to avoid confrontations with him for that purpose, but I guess it worked because it stuck for me. So let's apply it to this particular problem. The first thing we need to do is to identify what is A, what is B, and what is C. So if I match up the two formulas, A is the coefficient of the x squared term. In my equation, my variable is t, so capital A is whatever I have as the coefficient of my t squared term. And my coefficient of my t squared term is 1/2 of my acceleration. Right, so capital A in my equation is 1/2 little a. Right, it's the coefficient of t squared. Capital B in the quadratic is the coefficient of x to the first power. And that would be the coefficient of my t, and that term is v sub I. And finally, C in the equation is the constant. The constant in my equation, be careful, it's not just d, it's actually the opposite of d, because that's being subtracted instead of added. So C is minus d. And now the next step is to plug all that into the quadratic equation. So I'm left with, instead of x, it's going to be t, because that's my variable, is equal to the opposite of b, my b is v sub I, plus or minus the square root of b squared. And that would be v sub I squared minus 4 times a, which is 1/2 the acceleration, times c, which is minus d, all divided by 2a. That's 2 times a, which is 1/2 of the acceleration. And now I can do a little simplifying. If I look in the denominator, 2 times 1/2, the 2's are going to cancel. And if I look up in the numerator, inside the square root, I have minus 4 times 1/2 a times minus d. The minuses are going to cancel there, and that's going to become a positive. And 1/2 of 4 is the same thing as 2. So let's rewrite this. That gives me t is equal to minus v sub I plus or minus the square root of vi squared plus 2ad is what that simplifies to, all divided by a. So that made it a little bit neater and more compact. And now I'm ready to plug in some numbers. T is equal to minus v sub I, remember it was 3 meters per second, plus or minus the square root of v sub I squared, that's 3 meters per second squared, plus 2 times a was 9.80 meters per second squared, times d was 5 meters. And all that is divided by a, which is 9.8 meters per second squared. All right, so let's start working through some of the numbers here. On the numerator, I have negative 3 meters per second, plus or minus, inside that square root, I'm going to have 3 squared. 3 squared is just 9. Plus 2 times 9.8 times 5. 2 times 9.8 times 5, that's the same as 10 times 9.8, which is 98. So it's the square root of 9 plus 98, which is 107. So underneath the square root, I have 107. And if I look at the units, the meters per second, when I square that, that's the same as meters squared per second squared. And then when I take meters per second squared times meters in the next term, that also gives me meters squared per second squared. So when I add those two together, I still get meters squared per second squared. And then that's all divided by 9.8 meters per second squared. So what does that give me? That gives me negative 3 meters per second plus or minus the square root of 107. When I do that, square root of 107 is the same thing as about 10.34. And the square root of meters squared per second squared is just meters per second. That's all divided by our 9.8 meters per second squared. Now remember, when you're solving a quadratic, you always get 2 roots. There are always 2 different solutions. One using the plus sign and one using the minus sign. So let's start with the plus sign. If I take negative 3, I add it to 10.34. That gives me 7.34. And when I take 7.34 and divide it by 9.8, that gives me one possible root is 0.75, right? Positive 0.75. Let me write them up here. The one root is t equals 0.75. And if I check my units, let me fix that up so we can see it better here. T is 0.75. I think I'm slightly out of range there, so let me come to a new page and try this again. There we go. T equals 0.75. And if I check the units in the numerator, I had meters per second. On the denominator, I had meters per second squared. Dividing fractions, this is the same as inverting and multiplying. So that would be meters per second times seconds squared per meter. The meters cancel, one of the seconds cancel, and I'm left with seconds, which is what I expect to get when I'm solving for a time. So the one possibility is 3/4 of a second. But the other possibility is using the minus sign. So if we go back to the equation we were working with there, -3 minus 10.34 gives me -13.34. And if I divide that by 9.8, that gives me -1.36. Right, so that's the other possible root. -1.36 seconds. Now what that would physically mean is that the ball hits the ground 1.36 seconds before it left my hand. In other words, you can't have a negative time. That would mean that we're traveling backward in time, which isn't how the physical universe works. Therefore, our answer, the correct answer, should be 0.75 seconds. 3/4 of a second after it leaves my hand, it should hit the ground. Yeah, it takes a little bit of work to solve one of these quadratics, no question about it. Kind of messy to plug through the formula. If you have a graphics calculator, there's an easier approach that you can use to check your work. In fact, once you gain some experience with this, if you have a graphics calculator, I'll let you use this approach all the time. And that is to have your calculator solve the problem for you. Understand, though, that here at the beginning of the year, when we're specifically going to be testing on algebra, I would want to see all the steps for you to work through the quadratic formula and solve for the answer. If you want to use your calculator as a double check, that's fine, but I want to see the work worked out that you know how to do it. If you have a graphics calculator, you may find out that this application, this app, is already installed. If not, you can get the app from me. All right, we can download it for you onto your calculator, or you can go to Texas Instruments website and get it from there. To access it on your calculator, if you press the Apps button, that should bring up the list of applications you have installed in your calculator. And if you scroll all the way down to the P's, you're looking for an app called PolySimult, PLYSMULT2. It's a polynomial solver and a quadratic equation solver. If you have that, you can press Enter, and it'll open it. And press any key to continue. And from the main menu, we have a polynomial that we want to solve. We have a quadratic we want to solve. So pick choice number 1 there, Polyroot Finder. And then the first thing we have to do is to tell it what order of polynomial this is. A quadratic is a second order polynomial. The order is just the highest exponent of the unknown. And this equation, t is raised to the second power. That's the highest power in any term. Everything else should be okay by default. So I'm going to hit the next key, next button. And now what it's going to do is to ask me for the 3 coefficients in the equation. And if you notice, the first thing it asks me for, this a2, that's the coefficient of my squared term in the quadratic. And if you go back to our equation, the coefficient of our squared term was what we called capital A. And that was 1/2 of our acceleration. 1/2 of our acceleration. That is the coefficient of t squared. And 1/2 of the acceleration is just 0.5 times 9.8, because that was the acceleration. I'll press Enter there. That's the same as 4.9. And then the next thing it processing for is a1, which is the coefficient of the linear term. That would be the coefficient of t in our equation. And the coefficient of t was our initial velocity. That's what we called capital B. And our initial velocity was 3 meters per second, so I'm going to put that in, press Enter. And then finally it asks me for a sub 0. A sub 0 is just the constant in the equation. And that's what we called capital C. And our constant was the opposite of our distance. It was -5 meters. So I'm going to put in -5. Press Enter. And now that all the coefficients are in, I'm going to hit the Solve button. So I'm going to come up here, press Solve. And instantly it gives me the 2 roots. Notice the one possible solution is -1.36. That was the one that we said was physically impossible. but the other root, the positive 0.75, is exactly the same one that we calculated. Right, so with very, very minimal effort, it spits out the same roots that we got using the quadratic equation. So you're welcome to use that on a test, on a quiz, as a double check of your work. But I do need to see that you know how to work it out by hand because it's something that you should be able to do.